Okay, so just a quick review of what we did before. You have if the equation is to be solved on the interval a to b, then you have put n nodes on it. We'll call those x0 up to xn minus 1. x0 is a, xn minus 1 is b, and your spacing is b minus a divided by n minus 1. Okay, you have your forward difference and your backward difference and your central difference formulas. Okay. And now this time we'll use these differences to set up a functional, which we will then minimize. So let's say I wanted to solve the prototypical equation y prime equals y with 5 nodes on the interval 0 to 1. And then you'd get delta is equal to 1 over 4. And right, n minus 1 is 4, you get 0.25. And then you can label these, you can work out what the node values are. They're placed on the unit interval. And we're going to call the unknown values of the solution. Oh, okay, so I shouldn't really say the solution. I should say the approximate solution. At the nodes, we'll call those u0, u1 up to un minus 1. Okay, so if we said that y prime is equal to y, then the approximations for y prime on the subintervals between two adjacent nodes, those look like minus u1 plus u1 over delta, minus u1 plus u2 over delta, and so on. And we know we can have some choices about these are supposed to be equal to the function, to the approximated functions. So we could have a choice. We could set them equal to u0, or right, the first one we could set equal to u0 or to u1 perhaps. So I chose to use an average, u0 plus u1. And so then if we arrange them in a table, this is what the nodes, this is what I am saying. If I want to come up with with these approximations at these points on the interval for the approximate solution, those are the values. Then we get this table of equations if you use that discretization. There are other ones which are possible. And if you want a more compact notation, we define matrices like this, D0 and D1, right? The first one approximates the function on an interval. The next one approximates using a forward difference, the derivative on a subinterval. And we'll let u be the vector of these values of the approximate solution at those nodes. Okay, then the approximation can be written as d0u minus d1u. And I'll call d0 minus d1l. So that means lu is equal to 0. L equals d0 minus d1. Okay, now when do we have a solution? Well, if lu is equal to the 0 vector, that means that the norm of lu is 0. That means that the norm of lu squared is 0. The norm of lu squared is the inner product of lu with itself, and it's a convenience to divide that by 2. So if the inner product of lu with itself divided by 2 is equal to 0, then we would have an exact solution. Okay, we are not going to get an exact solution, so what we're going to do is we're going to try and get close to an exact solution. So this condition, lu with itself divided by 2 is equal to 0. I'm just going to try and make that f of u equals 1/2 lu inner product with itself. I'm going to try and make that as small as possible. And then I'm going to use this steepest descent scheme to do the problem. So if I take f of u, we have this, we can take f of u plus h, right? And what we will get is if you replace u by u plus h everywhere, and then you expand inner products in the usual way, and over here, you'll see that you're recovering your original inner product. And over here, note that X inner product with Y is the same as the inner product of Y with X in real vector spaces. So this is being repeated twice, so that's where the 1/2 is canceling out, right? So that's the symmetry property. And when you have something times H, inner product something times H, those terms are considered to be of order H squared. So H is some small, very small vector. And when you take inner products with itself, you get something that's really tiny. So what you get is f of u plus inner product LU LH plus terms of order H squared. Now, when you have these linear operators, you can think of them as matrices. When you bring them over to the other side in the inner product, right? Then you get the transpose, or the adjoint operator, right? Which, as in terms of matrices, that's a transpose. So you get f of u plus the inner product of L transpose LU, inner product with H, plus terms of order H squared. Now, in general, if you have a functional which has a gradient, then it has a Taylor series. F of u plus H equals f of u plus the inner product of what we call the gradient of f with H plus terms of order H squared. Okay, so if we identify this part here with this part here, okay, so the thing which is the inner product with H, this thing on the left-hand side here, that must be this gradient. So for this functional, the gradient in the standard inner product is L transpose LU. So now we can do steepest descent. Steepest descent is basically start from some given u, some estimate of the solution, and you get a better estimate of the solution, one which will produce a smaller functional value f of u by u minus lambda times the gradient for some positive step size lambda. Now, what you want to do with this is to vary your lambda, and that's called a line search technique. But I want to concentrate on the gradients in this session, so I'm not going to do that. I'm just going to talk about the gradients this time. Okay. So now it was studied by, this sort of issue was studied by Courant, Friedrichs, and Levi, and they came up with what's called the CFL condition today. And basically what this says is, if I were to double the number of nodes to try and get a better approximation, I would be having the internodal spacing, and I would have to reduce my lambda by a factor of 4. So on really fine grids, which hopefully give me a much better solution, I have to make my lambda so small that it isn't worth doing this. But we'll see how to fix that in a moment. Okay. So one way, as I said before, is this line search technique business. You vary your lambda. The other technique, or another technique, is to work out a better gradient, which we'll discuss in a moment. Okay, so if we, so how do we do this? How do we implement this in Python? Okay, okay, so before we do the implementation, on the theory part, are there any questions? Okay, so we'll move on to the implementation. Speak up if there's any issue. Import NumPy, we're going to use NumPy arrays. Remember these arrays, which I showed you for a small number, they have lots of zeros, right? And if you can imagine, say, 101 by 101 nodes, how many zeros there were. So there's really no point in keeping those zeros, and then later on you're going to multiply by these zeros. There's no point in doing all of that. So it's much better to work with sparse matrices. Okay. So we're going to import the SciPy dot sparse lets us do things with sparse matrices. Okay, let's use 11 nodes, and we're gonna linspace means give me an array with equally spaced nodes, starting with the value 0, stopping with the value 1. I want n of them. In this case, n is equal to 11, and I want you to return this equal spacing between the nodes. Otherwise, that is by default is set to false. So you're going to return a value, and I'm calling that value x, and I'm calling the arrays x, and I'm calling the spacing delta. Okay, so this matrix D0, it's n minus 1 by n. It's mostly 0, so I'll set it up first as zeros, and then I will the values here, which were supposed to be 1s, I do a for loop, and I set those up as 1s. So now I've set up the dense matrix. I don't want that. I want the sparse matrix. Okay, just before you do that, you're multiplying by a half. That gives you D0 as a dense matrix. Okay, but I would like to set it up as a sparse matrix. So I imported the sparse matrices as SP. So if I do SP D0, I'm going to set equal to a sparse matrix, and the storage format is CSR. Okay, there are different storage formats. This seems to be fairly common, so I'm using CSR. So store this as a sparse matrix using CSR storage, which matrix take A, which was the dense matrix, and now store it as a sparse matrix D0. Is that okay? All right, now let's set up D1. It's the same idea. It has n minus 1 by n. It dimensions n minus 1 by n. It's mostly zeros, so I'll start it off as being all zeros. And then I will go down, and the values which are supposed to be 1s and minus 1s in here, I set them up using a for loop. I change those zeros to 1s and minus 1s. And then I should divide by delta. Okay, so that's set up D1 in the format that I've shown you before as a dense matrix. I don't want to store that as a dense. I want to do all my calculations using sparse matrices. So I say SP, that was the sparse matrix packet module from Python. And I'm going to store that as a sparse matrix using the CSR format. Okay, it's stored as D1. Okay, I said L is equal to D0 minus D1 before. Okay, so that's L equals D0 minus D1. It understands that this is a sparse matrix now, since this operation is with sparse matrices. And I need its transpose. So what this does is, for CSR matrix, for sparse matrices which are stored in the CSR format, there's a method called transpose. So you're going to take the transpose of this L, and using sp.csr submatrix dot transpose, that acts on L, and I'm going to store that as L transpose. That's another sparse matrix. And I need, for my gradient, what was my gradient? It was L transpose times L. So I'm going to get L transpose times L. And this use of the, note this here, for the matrix multiplication, I'm using this @ symbol. So I think that's new in Python 3. I don't think it was in Python 2. And it allows you to, that basically does matrix multiplications and for different kinds of matrices, in fact. So it's quite useful. All right, so that's how we're writing matrix multiplication now, using the @ symbol. Some more compact notation than we've seen before in the course. Okay, now I'm ready to do steepest descent. What was steepest descent again? That was u gets replaced by u minus lambda times the gradient. And that hopefully gives you a u which gives you a smaller f of u. So we have to start from somewhere. So let's start with them all being ones. In this case, 0.0045 was about the lambda, the biggest lambda that I could use without it becoming unstable. We're going to run this until some error condition is met. Okay, count the number of steps. So what's the gradient? The gradient is L transpose L times U, we said. So how do we optimize U? We take U and we subtract off the step size times the gradient. My error condition, or my condition, will be the norm of the gradient. Okay, that lives in the linalg package inside of NumPy. Okay, so np.linalg.norm, that gives you the standard Euclidean norm for a vector. You could use other ones, so that would be fine. Okay, so that you count the number of steps. All right, so if I do this and I keep going until the gradient, the norm of the gradient is less than, I guess that's 10 to the minus 5. Then I keep doing that over and over again. And it took like 330 steps to do that. Okay, now I want to plot. So matplotlib.pyplot, that's PLT, and a plot on the horizontal axis the array X, and on the vertical axis the array U. Okay, so that's the result I get. And what do I want? I want something that looks like the initial value times e to the t, right? Yeah, sorry, e to the x. So the value that I'm getting is 1.428. Sorry, the value that I should get is 1.428, I guess. And the value that I'm actually getting is 1.429 for the last value of u. Okay. All right. Any questions there? Okay. Now let's try this with an initial value problem. So y prime of x is equal to y of 0 is equal to 1 on the interval 0 to 1. Now, the problem we had previously has in principle infinitely many solutions. How many solutions does this initial value problem have analytically? Think back to your differential equations course. How many solutions should this problem have?
So infinitely many solutions.
The first problem that we did had no condition. It had infinitely
G.
many solutions. How many
Yes, yes.
solutions does this have?
Achha, with condition, right?
With a
With
condition, it
condition,
should have only
unique solution hoga, one solution. Yeah, right.
one unique solution, right?
One unique solution.
Yeah. Okay. So once again, U is the set of the values of the approximate solution at those 5 nodes on the interval, let's say. And we know that the first one is going to be 1. Okay. So let's take that 1. Let's take 1 and the rest zeros out as a constant vector, plus then the vector is 0, and then there's these values u0, u2, u3, u4, or in general up to from u1 up to un minus 1. Okay, now let's call those values that are not fixed, that we don't know, let's call them v0, v1, v2, v3. And then I can write this, I can write it like this. There's a constant vector plus a linear map, P, and what P does is it acts on a vector V, which is of dimension n minus 1, and it prepends a 0 to it. Okay, right? So the action of P on V is to stick a 0 to the front. Is that okay? So I can write that as u is equal to c plus pv. So u has n values in it, and v has n minus 1 values. Those are the values that need to be determined. C is all zeros except for the initial condition at the beginning. Is that okay? Okay, so now if I think of f as not being a functional of v, but as being a functional of u, it's the same differential equation, right? As we had before. So f of v is 1/2 Lu inner product with Lu, but u is c, u is equal to c plus pv, right? Right? Maybe I should put that in. It's always better to have too much in your solution rather than too little. So, okay, so I'll replace u by c plus pv, and then this is what it looks like. Okay, so it's a compact, it's this constant vector lc plus lpv in a product with itself. Is that okay? All right, so now before, when I had f of u plus h, h is considered to be some small perturbation about u, and it's the same dimension as u. Now, I'm going to have a perturbation k about v. So it's supposed to be of the same dimension as v, all right? So it'll have n minus 1 terms in it, okay? And the reason I'm doing that is because I can't disturb the initial condition, right? The allowed perturbations about u should not disturb the initial conditions, which means you've only got a perturbation about v actually, which I'm going to call k, okay? So I'm going to have f of v plus k. So I replace v everywhere where I had v in this functional, I'm going to replace it by v plus k. And then I'm going to expand out. And then I'm going to do all that business with the using symmetries and orders of k squared this time. And so what I'm going to get is I'm going to get that this is f of v plus lc plus lpv inner product with lpk plus terms of order k squared. Now I want to have k by itself, right? So that I can use that Taylor series to work out what the gradient is. So I'm going to move this LP over here. And remember, when you move a matrix over to the other side, now you want the adjoint. And in terms of matrices, the adjoints are transposes. So when I move the LP, which is next to the K, over to the left-hand side, you have LP, it's transpose, not LP, but it's transpose times LC plus LPB, and now K is by itself. Okay? Also remember that AB transpose equals B transpose A transpose. So this becomes F of B plus K is F of B plus P transpose L transpose times LC plus LPB inner product with K plus terms of order K squared. Okay? So what would the Fourier, sorry, not the Fourier series, the Taylor series be? The Taylor series is f of v plus k is equal to f of v plus the inner product of the gradient with k plus order of k squared. So the gradient of f with respect to v is P transpose L transpose LC plus P transpose L transpose LPB. Okay? So instead of having a matrix times V, now you've got a constant plus a matrix times V. And that's what you'll get in question 4 of the midterm. Okay? All right. So let's define our C was all zeros except the first entry is 1. Our P, what was P? P was almost all zeros, except you've got these ones down here. So I'm going to use a for loop to set those all equal to 1. Oops. So you get P. So A is now P, but as a dense matrix. I want to store it as a sparse matrix. Do that. Now I also need P transpose. So transpose it, store it as PT. I'm going to need in my calculations P transpose L times C. That'll be some other constant vector. Oh, okay. So P transpose at LT at L at C. And I also need P transpose LP. That'll be a matrix. So I multiply that out. Okay. So we need an initial guess now for V. Remember, V is U with the initial condition thrown away. Okay. So let's start with all ones. And now what do? Well, here's the gradient that we have. P transpose LC plus P transpose LP times V. V minus the step size times the gradient optimizes V. Check the gradient and increase the step count, see what happens. Okay, so boy, that took a lot longer. Okay. Now if we want to see what happens, remember V didn't have that initial node value in it, so we have to add that initial node value. We concatenate 1, the array which consists only of 1 with the array V. And that gives me my U. Now I plot it, and I also plot the solution that I wanted. They're almost on top of each other, and if we compare the the values, they're not too bad. Okay. Another way to do it is that, remember, so in the calculus of variations, you calculate what we are calling the gradient, and then you set that equal to 0. And when you set that equal to 0, you call those the Euler-Lagrange equation. So basically, we're working out the Euler-Lagrange equations here. So this was the gradient, and I set it equal to 0, right? When the gradient's equal to 0, and we're using it in a numerical routine of steepest descent, then the descent would stop, right? Or we can look at it this way. When you take the derivative and you set it equal to 0, you're looking for the maximum or the minimum, right? So we set it equal to 0 while looking for the maximum. Okay, now, if we move this constant vector over to the other side, we get this. So all I need, in order to find the V, another way of doing it is just to solve this equation. P transpose LP acting on V is equal to minus this constant vector, whatever it is. So in order to do that, I'm working with, if I want to work with sparse matrices, and you always want to work with sparse matrices if possible, I should import the linear algebra module for sparse matrices. And so what am I going to do? I'm going to solve. This is the left-hand side here, and this is the constant vector on the right-hand side. So I'm going to ask for the solution. That gives me my V. Once again, I need to concatenate an initial 1 with that V. And now if I plot it, well, I get exactly the same results that I had before. Okay. All right. So John Neuberger showed that if we work with inner products, we can take different inner products. Those will give us different gradients. And Neuberger showed that it would be best if you think a little bit about the inner product, and then you can get gradients which have nicer numerical qualities. Okay, so there's some work that I've pointed you to by Mojave and Montgomery using their idea. What I'm going to do is I'm going to say that in this problem, look, I've got this L, right? Sorry, way up here, I guess. I have this L. So L is the important thing that's showing up. So I should use an inner product using L. And if I do that, if I do that, so what I'm going to do is there's a new inner product written with round brackets, V with W. That's the usual inner product, except instead of V with W, you have LPV inner product with LPW. Okay? So now, if I take f of b plus k, then it has another Taylor series. That's f of b plus the inner product of this new gradient with k, using the new inner product, plus terms of order k squared. But what's the new inner product? The new inner product says the inner product, you replace V and W with LPV and LPW. So you get this LP times the new gradient, inner product with LPK. And now I bring the LP over to the other side, which means I have to take the transpose of the product, which is the product of the transposes in the reverse order. So now, here is the new gradient in this new inner product space. And this is the new gradient. And this is the old gradient that we calculated before. So the relationship between the two of them is given by this equation. Okay? And what was the old gradient that we calculated before? That was this thing in the round brackets here on the right-hand side. So you have to take the inverse of P L transpose LP inverse times this old gradient, and that gives you the new gradient. Again, you never want to take matrix inverses if possible. You just want to be able to solve the equations. And we're using sparse matrices, so we're going to use the sparse matrix solver. So same as before, we calculate the old gradient. Then we calculate this new gradient. This is the new gradient by solving this equation. And I'm going to use the new gradient to do it. And I'm going to use a step size of 1, which is huge compared to the old step size. And what happens? You have convergence in a single step. Okay? So Mojave and Montgomery showed that for linear problems, this approach, this different gradient that you would get, gives you a solution in a single step. And in fact, this is exactly equivalent to what we did over here when we set the gradient equal to 0 and we solved. It was the same thing. Okay, so the choice of inner product when you're doing a gradient descent scheme, the choice of which inner product to use and therefore which gradient you will use. These are terribly important. Okay. So I figured some of you might still be working on the midterm. So I didn't think that we should do a very long lecture this time. Okay. So we'll stop here. Are there any questions?
No, sir. It's fine.
Okay. So if there are no questions, I or Riaz will see you on Friday.